This is session CMP 202, and we'll be talking about high-performance computing, HPC partner ecosystem at Google Cloud. You can submit your questions and comments on Dory, and if you're not familiar with Dory yet, you have a neighbor, turn to your left or turn to your right. We're sure there are some Dory experts in the audience. And also, did you know that you can also thumb up or thumb down some Dory comments or anybody else's Dory comments? And so the most popular Dory comments will be pushed up to the top of the queue, and that will really get our attention. So let's get it started. My name is Michelle Xu. I'm with Google Cloud's Global Technology Partnership team. My job is to make sure that Google Cloud and our partners work together and that we deliver solutions so the end users can adopt cloud easily, quickly, and cost effectively. And some of our partners are here today with me. Spoiler alert, we have a couple demos. So we'll begin with a personal story. I was an engineer, I was a graduate student. I studied optics, integrated circuits, optical communication, and then later atomic physics. So scientific computation is very much near and dear to my heart. And thinking back more than a decade ago when I was running simulations, I only really had a couple of choices, right? Either I run a very rudimentary simulation, compressed on my own desktop, or I can submit the 3D jobs, the very complex, the real problems into a data center, and then have to wait in a queue for a week. Time has changed. All of these machines are available at our fingertips. And why Google Cloud? Google's data center and our cloud has supported many businesses to grow, and some of these businesses are our own. You might know that we have a search engine, and we have a platform where people can share and publish videos, and we also help people to exchange emails. All of these businesses have grown over the years, and each business has more than 1 billion customers today. So our track record is pretty good, right? Our track record to help businesses to grow is pretty good. And there's no magic. It is all in the investment we have made in our data centers and our facilities. So underneath it all, we customize a lot of things. We customize bus tabs so we can supply a lot of power into our data center. We customize cooling systems. We even put machine learning so then our data center can run even more efficiently. So for example, let's take PUE, right? Power usage effectiveness. It is the ratio of the total amount of power you put into a data center divided by the amount of power consumed by IT equipment. So in the perfect world, PUE is what? 1, right? And now, if we take any data center around the world, the industry norm to run a data center is 1.5, which means every 1.5 power you put into the data center, and only 1 watt is used for IT equipment. And at Google, because of our investments, we're so good at running efficient data centers, our PUE is 1.1. In addition to the data center investment, we also want to make sure that our data centers are connected all around the world. So we invest in subsea optical cables, and here's a picture of our engineering team laying down the cables. There are total 13 of them around the world, and they're both underneath the Atlantic as well as the Pacific Oceans. And these cables are so long that we even need to put in repeaters so that we can repump the optical power periodically And the investment doesn't just stop there. In the past 3 years, we have invested $47 billion. We serve more than 1 billion IP addresses every day. We have 5,000 caching points, and our machine uptime is 4 nines. Here are some additional statistics about our infrastructure. We have 19 regions, and our track record is we have been growing 5 to 6 regions every year. Feel free to take a photo. Here's a visual, which is putting all of the statistics on this map. And the point about this, as I mentioned, time has changed. Engineers no longer need to worry about where the computers are, where they're located, what size they are, and then wait weeks in the queue. All of these machines, this entire infrastructure you're seeing here on the map, is available to you from your laptop. And the infrastructure is offered to you as services or products from Google Cloud. We have a wide category of compute, networking, storage products, software as a service, etc. And we're continuously making new products every day. And so this week, in the past couple of days, you might have already heard a lot of new product announcements. Instead of going through the entire catalog, I picked out a few that I thought this particular crowd might be interested. So during the keynote, we talked about 2 new machine types, C2 and M2. C2 is the compute-optimized compute engine that can go up to 3.8 gigahertz. And the M2 is a memory-optimized compute engine, and they can go up to 12 terabytes. So imagine, right, you have some scale-up, crazy simulations. These 2 machines might come in very, very handy. And knowing that our product catalog is pretty wide, so our product manager, Hanan, organized a session yesterday. So this is the second QR code. Organized a session yesterday to give you a walkthrough of our entire GCE product catalog, and also to show you how to pair each one of our machines to the specific use case that you're interested in. I picked the third talk, that is storage. And the storage is special because the storage focused on HPC systems. So again, you might be interested as well. And the last one I picked is on cost savings. That is always a hot topic. You may or may not have missed these sessions. If you have, that is okay, because they're going to be available online for you to look at. So with all of these services and tools available to you, you already have everything you need to run your HPC workloads. And if you're interested to, not DIY, but also choose a partner product, we also have a lot of partners in the HPC ecosystem that are currently working with us. So for example, we have systems integrator partners, we have storage partners, we have HPC application partners. And what we mean by HPC application is, for example, in CAE, you have Altair, right, a famous CAE vendor, or in EDA, we have Synopsys. And we also are working with job scheduler partners so that they can help us to manage the entire infrastructure for our customers. And today, we would like to show you, seeing is believing. We would like to show you a couple of our partner solutions. And let's jump into it. Google Cloud has made NVIDIA GPUs available through our platform. And in the past, I would not have imagined to be able to render anything on the cloud. And the way we enable GPU through our cloud is to make sure that we set up the GPUs in the pass-through mode, and so that the performance is bare metal performance. And also, because of the flexibility of the cloud, You can attach GPUs to any instances, and then you can mix match the configurations of your infrastructure. For example, a different memory, different CPU, and different NVIDIA SKU types. And here are a list of NVIDIA GPU types we have available on GCP. And each one of them is targeted for a very specific type of use case. For example, if you're looking at more memory-bound or compute-bound kind of problems, and you might want to pick a specific GPU that satisfies your need. And today, we actually have T4 SKU, GA today, and they're available globally in EMEA, America, as well as APAC. They're available in 8 regions, and so T4 is very good at solving memory-bound problems. And we'll have Edward here from NVIDIA demonstrating the power of T4.
Today, welcome by the way. Today we're going to show some of the power of using NVIDIA on Google Cloud. The demo we have to show you is a dwarf star explosion. And so you might use some large compute to take this radio telescope data to crunch it in FP64 using our Volta line or a Pascal line of supercompute GPUs. And then in this case here, we want to visualize it to get some insight. And so because NVIDIA has T4s in the cloud, I can spin up instances. And in this particular workload, it's a memory-bound problem to visualize it in a way to get insight. It's not a compute-bound problem. So the T4 is actually a perfect balance for that job, so I chose T4s. But it's a very large amount of data. It's a couple of terabytes that you need to be processing in real time to be able to visualize it. And so what we do is we use a NVIDIA product called Index, which is able to do volumetric rendering across many nodes and many GPUs. So I actually have 144 jobs running as a cluster. I make an instance group, and then I just click to deploy. I get 36 nodes of 4 T4s each, just pushed out into the cloud, and then I have a web server able to connect to it. So if we jump across to my laptop, I can show you a demo. And before I put the mic down, I'll just explain a little bit about what you're seeing here. So this is the data set we have, and the colors are matched to different frequencies that are detected by the radio telescope. And there's sort of 2 dimensions to that. We have the top coloring, which is how you want to visualize the frequency. And then the second dimension of that is for the given amount of energy of that particular frequency, that particular particle, we can change the color map as well. So I'll let Michelle speak to a little bit more about some of the astrophysics fun, and I'll start playing with it and showing you how you can see different components. It's more than just the visualization, right? Each of this diagram is being done using 144 blocks, think of it, cubes. But it's more than just making it look pretty, it's about finding insight. And so I'm going to show you how you can interactively do that by changing the parameters to see different interesting features.
So this is a supernova explosion, and you may or may not know the actual physics behind it. You know, when a star is dying near the end of its life, instead of just quietly going away, they explode. They could explode. And so what you're looking at is different type of elements and particles being thrown away from the center of the explosion. And I believe, yeah, I was highlighting certain part of the elements that's been, so from a physicist perspective, they can select different part of the spectrum to reveal on this live simulation. And so then they can know how different particles interact with each other, the trajectory of their ejection angles, profile, and all sorts of scientific insights they can gain from this live simulation. So here's a fun fact. Oh, this is great.
And this is someone who knows what they're doing.
Yeah, this is the Foley. That's a pre-recorded Foley compiled, 360 view of a supernova.
Yeah, so it's the same demo. It's just that it's with someone who knows what they're doing. So they're able to find the insights and have spectacularly found those components to show us.
And so a little fun fact, as you're watching this play live, so there's a star called Betelgeuse. It's only 600 light years away from us. And Betelgeuse is so big that when it experiences supernova, which scientists do believe is going to explode soonish, and when that happens in our lifetime, when everybody else is looking at this bright blob in the sky, and all of us here, we can be saying, been there, done that. We've seen that at Google Cloud Next, right, in 2019.
Thanks very much.
That was amazing. Everyone give a round of applause for Edward and NVIDIA. It was beautiful. Cool. That was one of many amazing things we can do with GPU in the cloud. We have more than 600 GPU Accelerated apps available on our marketplace. And all of these apps are categorized into different verticals. And at Google Cloud, we have different vertical teams that are very specialized and knowledgeable about how the workload in each one of these categories work. And so I'd love to hear from you after the talk, connect, and I would love to introduce you to our area and domain experts so they can help you to identify how to best run your workload on Google Cloud. And out of these 600 GPU Accelerated HPC apps, more than 50 of them are in containers, right? We all like containers because, you build ones, run everywhere, easy to deploy, easy to manage. Here's our second demo from a couple of partners, actually. Do we all know what preemptible VMs are? Can I see a show of hands? Preemptible VMs? Nice, good, nice. For those who don't know what preemptible VM is, the name itself is quite self-explanatory. There's a trade-off, right? You can spawn a VM, and with preemptible VMs, there's a trade-off. You can take risk of jobs being preempted, and at the same time, you can enjoy the cost saving of these preemptible VMs. And I can see some of people are already shaking their heads because, engineers do not want to launch thousands of batch jobs and wake up in the morning knowing that jobs are not done. When we set up our entire infrastructure with a good scheduler and a good file system in the back end, even when the VMs are preempted, the job scheduler can recognize the jobs that are being preempted and save the current state of the job in the file system in the back end, and then put the job back in the queue and respawn it somewhere else and remount the file system. And let's welcome David from Elastifile and Brian from SCEDMD to show us how to seamlessly manage your preempted jobs on Google Cloud.
Thanks, Michelle. So we are going to show you today, to put it in context, this last year, Christmas happened in December, like it does every year. And I had something interesting happen. I've been married for 20 years, and so my 20th Christmas with my bride, and I got a gift that I never expected to receive on Christmas. Usually it's a sweater or socks or something like that. And this year I opened this package and I got a Rustler 4x4 VXL brushless Traxxas remote control car. Amazing, right? I did not expect this, thank you. And that's a reward for 20 years of marriage, I guess. But it was really fun, a toy, I have children, but something I could play with and it would be amazing. So I live in the great white north of Minnesota where it's snowy all the time. So I took this out over the last few months and put it to work. And I want to show you what it looks like when it runs. All right, tons of fun. We had a great time playing with these toys. So later that weekend, my 17-year-old son said, let me play with it. So right behind what you just saw is a hockey rink, which is pure ice if you don't live in a place that's cold. So he goes out, the sun's coming down, and he's ripping away with the car, and he gets like kind of into the distance, and all of a sudden I hear a thud, and it stops, right? No good. Everything was broken. He ran straight into a fire hydrant at probably 40 miles an hour, right? So I take the car home, and I want to fix it, and I'm pretty good at fixing cars. I've been doing this my whole life. I have a whole garage full of tools, and nothing works. Everything's miniature. I don't have no replacement parts. I have no tools that fit these little, tiny screws and everything. So I'm out of commission for several weeks, and I had to go get schematics and figure out how to rebuild these systems. I had to go order tools and replacement parts and all of that. And so essentially 3-4 weeks later, I had built an entire tool bench to manage this gift that I got for Christmas. But I got it back up and running, better than ever, and it's amazing and doing great today. So I share this story with you because I think it's consistent with the experience I've heard from a lot of our customers that we worked with as they've tried to take high-performance applications from how they're running on Prem today and into the cloud. And we get really excited about the engine, the tools, the preemptible VMs and containers and automatic scheduling, all this great stuff that can happen in the cloud. And often we get there and we get started, and then we figure out my tools in my garage aren't quite compatible with what's out there in the cloud. So we came together, and this is really what we've been working on jointly with Google Cloud, with the SCAD-MD folks, with Slurm and Elastifile. We're really here to take a lot of that complexity out of the equation and try to shorten the gap between what you do today and what you might do in cloud. And so we want to show you how this works. We put together a demo that's sort of simply architected like this. It's running in a Google project completely. Slurm will be stood up. We're going to deploy a whole bunch of VMs, preemptible VMs actually. We'll use Elastifile for the back-end storage, and we actually have an application that we authored called eRun, which does a pretty intense type of storage load generation, and we're going to show you what happens as we go. Okay, so I want to have Brian come up, and he's going to, actually not yet. So let me break down the components real quickly for you that are going to happen. So on the Elastifile side, if you don't know us, what we are is essentially a scale-out file system that's designed to operate essentially natively inside of Google Cloud. Okay, it presents as an NFS server, really simple, no client-side software needed, standard NFS you've been using for 10, 20, 30 years. But on the back end, it's a highly distributed file system that handles embarrassingly parallel connections really well. It runs completely inside of Google Cloud, so any region, any zone, it can stand up and run in a mere matter of minutes. The system, like I said, it's NFS v3. It's designed to handle its scale out, so as you need more capacity, you scale horizontally. You need more performance, you scale horizontally. And then when you're done with that performance and capacity, you can shrink it back in, which actually works. It's elastics in and out. So it's designed to get to large capacities, integrated with Google Cloud Storage, so it can tier. As your data gets cooler and you don't want to move it into a different place, you can just cool it off. It'll push the inactive files into cloud storage, but keep the entire namespace populated so the applications still see all their data. It's a highly available system if that's important to you. You can either run it in a single zone or many zones in a region or all the zones in a region and even do asynchronous replication across zones. Upgrades are automatic and non-disruptive. And then tiering, as I said, we can tier active data into cloud storage. You can also take snapshots of data and store them directly into Google Cloud Storage, which is a great thing. If you use storage on premises, the traditional filers often you have to reserve a big chunk of your data for redundancy and another big chunk of your capacity for snapshots. In this case, we can keep all of the performance capacity, which in our case runs completely in Google Cloud Engine, and then any data for snapshots can be stored into GCS at a lower cost and keep all of your primary tier available for performance. Okay, lastly, there's a capability called Cloud Connect, which is a data shipper for moving data in and out of cloud. This helps solve some of the gap when I have a large data set on-prem and I'm trying to figure out how to get it into cloud. We can move all of that, and we keep all the POSIX stuff as POSIX, M-time, A-time, C-time, ACLs, any of the metadata, and so even to the point where we can capture hard links and soft links. Essentially take a full snapshot of a data set, drop it in Google, and start operating, okay? So you have two options. You can deploy this in your projects, you manage it, we support it, or fully managed service, which has effectively gone to a self-service mode over the last week. Both of these accessible through Google Marketplace. The QR codes will get you there. Click the link, hit go, and you're up and running within a few minutes. As a matter of fact, Brian, who's going to come up now and talk about Slurm, he actually, during the demo, used the service to do the implementation. So let me hand off to Brian.
Okay, thanks, Dave. So I'm Brian Christiansen. I'm with SCEDMD. We are the maintainers of the open source workload manager / job scheduler. So a little bit about Slurm. Traditionally, we find Slurm in the more on the on-premise side. So, for example, Slurm's five of the top 10 biggest HPC systems in the world, and then also when we're going up into the top 100, we're on 40% of the top 100. So Slurm scheduling a wide range of use cases, going from capability to capacity machines, and also scheduling a hybrid of those workloads. For example, we've got a customer that does 14,000 jobs a minute in a high throughput environment. So a little bit about Slurm in the cloud and where does it fit. So a couple options of Slurm in the cloud is, one, you could have Slurm as a standalone clustered all in GCP. So you have your controller, your login nodes, and all your compute nodes. And then Slurm has auto-scaling capability. So it'll automatically create and delete VM instances in GCP according to the workload. And then also, so if you've got an on-premise system, you could just burst out into GCP, just extra compute nodes there, and using the auto-scaling capabilities there. And then a hybrid solution of the two is having your on-premise cluster and a cluster in the cloud, and be able to schedule jobs, submit jobs between the two. And so we've been working with Google to make it easy to set up a Slurm cluster in the cloud easier, and that's this repo, the Slurm GCP repo. So, okay, so we're going to jump into the demo that Dave and I created. So as Dave explained, in the demo we're going to set up an Elastifile cluster, a Slurm cluster, and submit a whole bunch of jobs and watch them run. So we'll show how easy it is to do. Okay, so this is the Elastifile as a service. We're going to go ahead and create that from the marketplace. We're just going to go ahead and give it a name, choose our region and the zone. We're going to head into the east. And then there's some profiles that just kind of give you some base options, how much capacity. And then we're going to choose the network that it's going to reside in. So we're going to do the default one. So we're going to so that's going to go ahead and create. We're going to spin it up. And the important thing that we're looking for right now is this share name. This is the mount point that we're going to mount inside of our instances. So Elastifile is done. We're going to go ahead and create our Slurm cluster. We're going to go to the repo that we just saw, clone it, and then set up the configuration file. And inside the configuration file, so I'm going to set it up so that we've got 1,000 nodes that we can burst out into. And since the Elastifile cluster is in the east, we're going to go ahead and put the cluster there. And our network was the default one. If you don't do the default, the deployment manager will actually create its own network for it. And we're going to do 8 just to get a bigger bandwidth. And preemptible bursting, that's so that any node that gets bursted out to is going to be a preemptible VM. And then this is just for Slurm accounting, so that it'll run my jobs using my email address when I SSH in. Okay, so we're going to do a little bit, just a little bit more setup. So taking that mount point, this is a script that's gonna mount the Elastifile service inside the instances and install some things for the E-run that Dave talked about. This is the load generator created by Elastifile. And then we're gonna go ahead and copy that into the deployment scripts. And so when we create the deployment, they'll get pushed up. Okay, so we use Deployment Manager to create the instances. You're going to see in Deployment Manager, we created a router, an instance for the controller, an instance for the login node, and you'll also see a instance that is the compute image. So what the compute image is that it's going to be a dummy compute node, and once it gets installed, then we're going to make a snapshot of itself, create an image of it, and then anytime we burst out, we're going to use that image so that we can start up VMs a lot quicker. Okay, so I'm just logging into the controller. We'll see all the make installs. Down here on the bottom right, I'm SCPing up just the script to do the E-run and my tmux.conf. Okay, once that's finished installing, I'm just going out to the login node where we're going to run the job from, and just set up some monitoring on the side. But so here on the right, I'm going to go into the images page, and you'll see that the compute image is creating. Once that is completed, so while it's building, until it's done completing, Slurm has marked the controller or the queue or the partition as in a down state, so no jobs can run on it. But we see that the nodes are up, or we see that Slurm's available to run jobs, but it's not in a state to run them yet until this compute image finishes. Once it finishes, it calls home and marks the queue and the partition in an up state so it can run jobs. And once it's up, the compute image will delete itself and will go away. So here we see that the Elastifile mount has been mounted inside at least the login instance, and it's been mounted across everywhere. So right here I'm submitting a job that's going to run on 10 nodes. It's just going to run host name on 10 different nodes. And it takes about 49 seconds to finish there. And so this will scale out about every 1,000 nodes. We have to back off a little bit because we're hitting API limits, but we can spin up about 5,000 nodes in 7 minutes. Here, I'm going to go ahead and submit the E-run script, and this is an array job, and it's going to be basically it's 1,000 jobs. We're going to spin up 1,000 jobs, and each job is going to be on its own compute node. So we'll see all the nodes have been fanned out. They're starting up. We see all the compute nodes being created. And on the left, we're just waiting for them to check in with Slurm. And once they check in, and while they're checking in, Slurm is starting the jobs. So you can see over here on the Elastifile graphs that they're starting to filter in, or starting to run. And then we speed up. And what you're going to see next is a couple of these VMs are going to get preempted. Slurm's going to detect that the VMs have been preempted. Jobs are going to get re-queued. Jobs that were on those nodes got re-queued. And so they become eligible to run after 2 minutes. And then Slurm will we go ahead and restart the instances when they've been preempted. And then these jobs are eligible to either run on the node it could run on that node that was preempted, or it could fan out, or it could spawn more nodes to run on. So it's right here. So right now we've run our jobs. They were 10-minute jobs. And now we're going into the tail of it, and this is just finishing off the preemptibles, the preemptible jobs. And then what we're also going to see too is all these compute nodes are going to clean themselves off. After they've been idle for a default of 5 minutes, Slurm will start tearing them down. So we spun up 1,000 nodes, and they all checked in within about 3 minutes, and they completed and then the preemptibles tailed off. So pretty simple to set up an Elastophile cluster and a Slurm cluster in GCP.
Right on, yeah. And actually, Brian did all that work pretty much by himself. He, when we started coordinating the demo, he went and grabbed, I showed him how to find Elastophile, and then he came back and said, okay, I already built all of it, and it all works. So a testament of an end user to a large extent. So essentially what we just saw, to recap that, is, as Brian said, 3 minutes, we had 1,000 jobs queued and another 1,000 machines created. And as you saw, as they showed up, work was starting to fly through the system. So super fast. And even the job, we sped it up a little bit for time's sake. You know, no one wants to watch a cake cooking, but in that short amount of time, I think it was up for 15 minutes maybe total from start to finish. About 1% of the 1,000 machines were preempted. And a preemptible machine lasts for max 24 hours, right? Whether it's a GPU or CPU based. But even still, in that short amount of time, they were lost. And so we did a session with an HPC session last year with Silicon Therapeutics using GPUs that were preemptible, and they didn't have this feature. You guys hadn't released your feature yet with Slurm, and so every day he had to go in and re-queue all these jobs with a manual, process to find what broke and fix it all. So that's a really great thing. And then most importantly, if you've ever been caught in the cloud issue, which is a month later, I forgot to turn off all these machines, Slurm prevents all of that. It left no trace. As soon as the jobs are idle, it cleaned them up, and the billing stops immediately, which is great. Your accountants will like that. So 1,000 machines spun up, parallel NFS running, very simple configuration. He didn't have to install any storage stuff. It just works out of the box. We were sustaining 2.5 gigabytes of sustained throughput through the system, and all of the data that was written in those jobs was persisted, even though when a preemptible goes down, the data gets deleted. So that's the net of that. We took preemptible machines, which by nature are non-persistent and unpredictable in when they're going to go up and down, and we eliminated the unpredictability of the non-persistence of data. We added Slurm and added this extra predictability and sort of accounting cleanup, right? So we could deliver reliability and predictability for HPC. Lastly, the question is, hey, that's great, but what's the cost? And so we ran the numbers to make sure that this is actually achievable, and essentially the cost impact is negligible. If you look at the total cost when running large HPC systems, most of it is compute oriented. So if you compare a standard compute-based system to preemptibles, typically they're about 80% less expensive. You add in Slurm and Elastophile. We did a model over a week, and it was just a few percent difference in the total price. So your savings are still 75 to 79% over what a standard deployment would look like. Michelle?
Yeah, thank you.
You're welcome.
Thank you, guys. Now we all know how to utilize the cost savings of the beauty of preemptible machines, as well as getting our job done in a timely fashion. And if you'd like to learn more about Elastophile, take a photo of this. We'll have a session tomorrow. All right. Oh, sorry. There you go. Let me wrap this session with a user story. This user is extremely special to us because it is our own engineering design team, our own semiconductor chip team. And that's why we call this story a Google on Google story. Although this is a Google semiconductor chip engineering team, but our engineering team resonates, that they have the same problems They design based on same principles. They use the same tools as everybody else in the world. So in case you're not familiar with semiconductor chip design, right? You lay out a hardware design, and then you put in some boundary conditions, input conditions, and you simulate the design first. When you're happy with the final simulation results, you send that blueprint to a manufacturer to be manufactured. And then the manufacturers send the sample chips back, and you measure them, and to see if the results are exactly how you designed it, and the results are what you're expecting. If not, likely you have to go back and retweak the design, right? And then send it back to the factory, now probably beta, and then factory send the sample chip back, you measure it again. So this whole iteration takes 1 year, 2 years, easily, several years, easily. So our own chip design team is thinking there has to be a way where we can reduce the engineering design cycle. And so they decided to move to the cloud. And just like everybody else in the world, they're thinking, we don't want to refactor our workflow. We do not want to retool our system. And at the same time, we want all of the benefits from the cloud. So in the early stage of their workload migration, they've decided that, okay, we'll keep our interactive sessions on-prem, and we'll keep majority of our repositories on-prem. And now when it comes to batch jobs, right, we need to launch thousands of them, and we don't even have this amount of machine on premises, so we'll do that in the cloud. And if you're familiar with, semiconductor chip design, or if you have paid attention to some of the jobs you have ran in the past, you will notice that some jobs require more CPUs, some require more frequency, some require more memory. And so our own design team, when they looked at the profile of the jobs, they decided to use custom machine types, which is a product that's available in Google Cloud today. So custom machine types really is a cost-saving play, right? So you don't over-provision. And then they were using containers because, it's easy to deploy, easy to manage. And our own team is also, as we just saw in the demo earlier by Elastophile as well as Slurm, we saw that if we're able to manage preemptible VMs properly, we can actually have quite a bit of cost saving and also be very efficient with our engineering design cycle. And lastly, and probably the most importantly, is security and compliance. Those hardware layouts are extremely sensitive, and our team has the same concerns as everybody else in the world. So I'll flash this very high-level architectural design that our own team's deployment has today in Google Cloud. On the left is their on-premises deployment. It's standard compute plus some storage components, and it's connected to Google Cloud through VPN. And in their cloud, they will stage their jobs, when it comes to job staging, right? You have your design files, inputs, parameters, boundary conditions, all loaded in cloud storage. And then they will have different persistent disks to load different design tools. And then eventually, all the computation is done in either custom machine types, containers, or just normal VMs that are available on Google Cloud today. And so this work was actually done before the C2 and M2s were announced or made available to our customers. So, the C2 are the high frequency one, the M2 is a 12 terabyte machine. So I highly suspect our own team might go in and try our own C2 and M2 machines very soon. So that is all the content we have today for everyone, and thank you for joining us. And so to recap, we are no longer limited by what computers we have in our labs. We're no longer limited by where the computers are. Time has changed. We're in an era where engineers are empowered. We're more efficient at what we do. And so we can clear our room in our schedules, right? So we can solve more problems and make bigger impacts in the world. Thank you. We have a HPC link here if you want to check out the content and assets we have today.